Now, part C is asking for points sufficiently close to the origin, show that the electric field magnitude is approximately proportional to the distance between the origin and the point of interest. So what is that distance? That distance is x. So for those points that are close enough to the center of the disk, we want to show that the magnitude of the electric field is proportional to x. And it's also asking how close is sufficiently close. When it says that in a physics problem, it means compare x to a variable in the problem, and it should be much smaller than that variable. Now, what would that variable be? If we want point P to be really close to the disk, that means the distance between point P and the center of the disk should be smaller than the size of the disk. And in this problem, the size of the disk is represented by variables capital R1 and R2. So in other words, they're saying for x much smaller than R1 and R2, show that electric field magnitude is approximately proportional to x. So then here's how we solve this problem. For x much smaller than R1 and much smaller than R2, x squared plus R1 squared is approximately equal to R1 squared, and x squared plus R2 squared is going to be approximately equal to R2 squared. So it's as if we're replacing x with 0, but note that we can't do that everywhere. We have an x in the numerator, we can't put x for that. In that case, the whole electric field magnitude will be 0. So that we can't do. Only in places where x is being added to R1 or subtracted. And likewise with R2, if we have R2 plus x or R2 minus x, in expressions like that, we can set x is equal to 0. We can also do that if we're adding, the squares of those variables. So x squared plus R1 squared, again, because x squared is much smaller than R1 squared, and these two values are being added, that is, adding x squared won't make much of a difference. So that's the idea. That's why we can set x squared plus R1 squared approximately equal to R1 squared, because R1 is much greater than x. Adding x squared to R1 squared is not going to make much of a difference. And same for R2, of course, same idea. Now let's rewrite this expression. Here's what we get. Note that the terms in parentheses can be simplified further. R1 and R2 will come out of the square root. So let me rewrite the expression with all the constants on one side and then x. And here's our final result. We were able to reduce the expression for the electric field magnitude to some constant times x. In part D, we place a point particle somewhere on the x-axis, really close to the origin, and that particle has mass m and charge negative q. So this is a negatively charged particle. What's going to happen is that the particle is going to oscillate up and down, because when it's above the origin, there will be a net force pulling the particle towards the origin. It'll accelerate towards the origin, go past the origin, and when it's on the other side, on the negative x direction, in other words, on the negative x-axis that is below the origin, there's going to be a net force in the positive x direction, again pulling the particle back towards the origin. We'd like to calculate the frequency of oscillations for this particle. And again, how do I know that the particle initially is very close to the origin? Well, the problem is saying that the particle is placed at x equals 0.01 R1. So this is the case with x much smaller than R1, meaning we can use our result from part C. Now let's go ahead and find an expression for the magnitude of the force, or actually the force acting on this particle. The force acting on the particle is equal to the charge of the particle times the electric field. And I have a vector equation here. This is telling me that the direction of the force will be the opposite the direction of the electric field. Now the electric field direction is the same as the direction of x. Whenever x is positive, electric field points up. And when x is positive, then the force is going to be pointing down. So above the origin, the force is going to point down. Below the origin, the force is going to point upward. Now let's substitute the expression that we found in part C for the electric field. To find the frequency of oscillations, we are going to compare this formula for force with the force in Hooke's law. Remember, that is the force applied by a spring. You may remember that force from Physics 1. And this is what it looks like. F equals negative k times x, where k is the spring constant. And the frequency of oscillations depends on two things. It depends on the spring constant k, and it also depends on the particle that is oscillating, the mass of the particle that is oscillating, mass m. So then comparing these two expressions, I'm going to set this whole thing here, this whole thing, equal to spring constant k. So that whole thing that I circled here, this expression, acts like a spring constant for this system of uniformly charged disk, positively charged disk, and the negatively charged particle oscillating up and down near the center of the disk. Again, from Physics 1, frequency of oscillations is equal to 1 over 2 pi square root of k over m, with k being the spring constant and m being the mass of the particle that is oscillating. So I am going to substitute for k the effective spring constant that I was able to identify in the expression for force acting on the negatively charged particle. And here's my final result. So I highlighted the expression that represents k in pink, so you can compare the two expressions. I just added a factor of m to the denominator, that's k divided by m in square root, and then we multiply that by 1 over 2 pi to get the frequency of oscillations.